Welcome back to the deep dive. Today we're tackling something really central in AI right now. How do we actually know if a large language model, an LLM, can handle complex real-world tasks, not just chat, but actually do things using tools?
It's a critical question. In our source material today, this paper, MCP-Bench, Benchmarking Tool Using LLM Agents, it provides some fascinating answers.
Right. It's like this paper acts as a guide, showing us maybe where the old tests fell short and presenting a much tougher, more realistic obstacle course for these AI agents.
It lays out a framework, MCP-Bench, designed to evaluate how well these agents plan, reason, and actually use external tools when faced with messy, real-world type problems.
Okay, so here's the plan for this deep dive. First, we need to understand why a new benchmark was even needed. What were the problems with the old ways of testing?
Yeah, the limitations.
Then we'll introduce you to this MCP bench approach, what makes it different, what makes it hopefully better.
And finally, the really interesting part, what did the research find? How are the top LLMs actually doing on these complex tasks?
You should walk away with a much clearer idea of what a tool using LLM agent is supposed to be and what it really takes for them to succeed out there. So let's start with the why. Before MCP bench, how were people evaluating these agents? The paper suggests there were some, well, significant gaps.
There really were. If you look at earlier benchmarks, things like ToolBench or BFCL v3, they gathered a lot of APIs, sure.
Sounds good on the surface.
But the APIs themselves were often designed for very narrow, isolated functions. So the tasks often ended up being quite simple, maybe just a couple of tool calls.
So not really testing complex reasoning.
Not deeply. Or you'd have situations where researchers had to kind of artificially force tools to work together because their inputs and outputs just didn't actually line up.
Like trying to connect pipes that weren't meant to fit?
That's a good way to think about it. It didn't capture the natural flow, the dependencies you see in real tasks.
Okay.
And even other benchmarks like Bench, which tried to use more compatible APIs, they often had limited scope, maybe just a few domains, a small set of tools.
So not enough variety.
Right. It made it hard to create diverse tasks or simulate workflows that cross different areas, like finance and travel planning. And they really weren't good at testing long-term planning or dealing with those complex dependency chains.
And then there were benchmarks using this. MCP, Model Context Protocol. That sounds promising.
It was a step forward. MCP provides a standardized way for the LLM to talk to different tools and servers. Think of it like a universal adapter.
Okay. Simplifies the communication part.
It does. And benchmarks like MCP Radar and MCP Vival used it. But again, they were often quite narrow. Just a few servers, maybe a dozen or so tools.
So still limited complexity.
Yes. The workflows tended to be short. Maybe fetch some information, then summarize it. Often they'd even tell the agent exactly which tool to use.
Which isn't very realistic.
Not at all. They didn't challenge the agent to figure out the right tools from a fuzzy request, like a person would give, or handle things like multiple goals, or needing to base decisions only on retrieved info that's information grounding.
Right. You mentioned information grounding. Can you quickly explain why that's tricky?
Sure. It means the agent can't just rely on its general knowledge. If it looks up flight times, it must use those specific times for the next step, say, booking a hotel nearby. It can't just assume or hallucinate details.
So it needs to stick to the facts it just found.
And these earlier benchmarks also didn't really push cross-domain orchestration using tools from, say, science and finance in one single task.
Okay, so it sounds like the existing tests were, well, maybe a bit too easy or too artificial. They weren't capturing the real challenges.
That's the core argument. There was a clear need for something more comprehensive, more realistic, and that's where MCP-Bench comes in.
This is where it gets really interesting. Tell us about MCP-Bench.
Well, MCP-Bench is designed to be much larger scale. It connects the LLM agents to 28 different live MCP servers.
28, okay.
And those servers expose a total of 250 tools. These aren't just random tools either. They cover a wide range of real-world areas: finance, travel, scientific computing, academic research, lots of practical domains.
250 tools across 28 servers. That is a significant jump in scale from what you described earlier. What does that enable?
It allows for building much more authentic tasks. Tasks with multiple steps, where the output of one tool genuinely feeds into the input of another.
Real dependencies.
Real dependencies. And importantly, within each MCP server, the tools are often complementary. They're designed to work together. Like a server for science might have tools for loading data, doing calculations, and visualizing results.
So tools that naturally sit together within a domain.
Exactly. It encourages realistic workflows within a server. And because everything uses that standard MCP protocol we mentioned,
Universal adapter.
right, it makes it much easier to build tasks that jump between servers too. Complex, multi-hop workflows that might involve, say, searching for academic papers on one server, then using a calculation tool on another.
So it's not just a bigger toolbox, it's an integrated ecosystem of tools designed for complex projects, potentially crossing different fields. That feels much closer to real-world problem solving.
That's the goal.
Okay, so you have this big integrated environment, but how do you actually create the challenging tasks for the LLMs? And then how do you measure success or failure? The paper mentioned a specific pipeline for this.
Yes, the task synthesis process is quite clever. It starts by looking at the potential dependency chains between tools. How can tool A's output be used by tool B and then tool C?
Mapping out the possible workflows.
Those chains become the backbone for creating complex tasks, but then comes a really crucial step they call task description fuzzing.
Fuzzing, what does that mean here? Is it like testing for bugs?
Not quite like software fuzzing. Here, it means taking a detailed step-by-step instruction and deliberately making it, well, fuzzy, more conversational.
How so?
They remove the explicit tool names and the exact execution steps, so the agent gets a request that sounds more like how a person would ask for help.
Can you give an example?
Sure. Instead of saying, use the Park Finder tool with criteria X, then use the weather tool for that location, the fuzzy request might be something like, I want to plan a weekend hike. Can you help me find suitable parks near me and check the weather forecast for them?
So the agent has to infer which tools are needed, the park finder, the weather tool, and in what order, just from the general request.
That's it. It forces the agent to reason about the user's intent and the available tools, not just follow explicit directions. The paper has some great examples, like a complex request about melanoma research or planning a multi-day hiking trip.
That sounds much more challenging.
It is, and they also filter these generated tasks automatically to make sure they're actually solvable and, make sense practically.
Okay, so that's how tasks are created. What about evaluation? How do they judge if the agent did a good job?
They use a two-tier approach. First, there are rule-based checks. Pretty straightforward stuff. Did the agent use valid tool names? Did it follow the correct format, the schema? Did the tool run successfully? Did it respect the dependencies?
So checking the basic mechanics, the execution quality?
Right. Did it follow the rules of engagement, essentially? But the second tier is where the deeper evaluation happens.
Breaches.
They use another LLM as a judge. This judge, LLM, is given the agent's interaction log and scores its performance on three main dimensions.
What are those dimensions?
First, task completion quality. Did it actually achieve the goal? Second, the rationale behind tool selection and use. Did it pick the right tools for the right reasons? And third, planning effectiveness. How well did it structure the workflow, handle dependencies, and maybe even parallelize steps if possible?
Okay, so judging the strategy and the outcome.
And it looks at sub-aspects like grounding the answers in retrieved information, getting parameters right, awareness of dependencies, and overall efficiency.
The paper also mentions something about prompt shuffling for this LLM judge. Why do that?
That's to improve fairness and reliability.
Yeah.
They found that LLM judges, like humans sometimes, can be influenced by the order in which criteria are presented.
Order matters.
Apparently so. So they randomly shuffle the order of the evaluation criteria in the prompt they give the judge LLM. They do this multiple times for each task and average the scores.
So mixing it up reduces bias from the order.
That's the idea. The study showed it made the judgments more consistent and more closely aligned with human evaluations. It makes the scores more robust.
Okay, that sounds like a very rigorous approach, both for creating tasks and for evaluating them. So the big question, they ran this. They tested 20 different state-of-the-art LLMs on over 100 of these complex tasks. What did they find out? What are the key takeaways?
Several things really stand out from the results. First, the basics seem to be largely handled now. Things like understanding the tool's format, using the right names, schema compliant.
The first tier of evaluation you mentioned?
Right. Even pretty average models were getting over 95% accuracy on those aspects. It suggests that just getting the mechanics of tool use right isn't the main hurdle anymore for most decent models.
Okay, that's good news. But I sense a but coming.
There is a but. While the basics have converged, huge differences appear when you look at the higher order reasoning, especially planning.
The second tier stuff.
Yes. The top models, they mentioned GPT-5 and O3, specifically in the source, showed much stronger abilities in structuring their approach, understanding dependencies between steps, and even reflecting and correcting course if needed. Their scores in those planning areas were around, say, zero point 0.7 out of 1.
And the others.
Weaker models really struggled there, often scoring below zero point 0.3. It starkly highlights that long-term planning, coordinating multiple tool uses over many steps, that remains a major challenge.
So knowing how to use a wrench is one thing, but knowing when to use the wrench, the screwdriver, and the hammer, and in what sequence to build the cabinet, that's the hard part.
That's a fair analogy. It's the strategic thinking, the orchestration, that separates the leaders from the pack.
What else did they find?
Scalability was another differentiator. How well do models cope when tasks involve multiple servers and potentially more tools?
Does performance drop off?
For some, yes. The top models like GPT-5 and o3 seem to maintain their performance levels reasonably well, whether it was a single server or a multi-server task. But weaker models, they used Llama 3.1 AP Instruct as an example, showed a noticeable drop in their overall scores when moving to multi-server tasks.
Interesting. So handling that distributed complexity is tough for some models.
It seems to be a key capability of the more advanced agents. They're more robust when the problem space gets bigger and more distributed.
And efficiency. Did they look at how many steps or calls the agents needed?
They did, and the differences were quite striking. Some of the weaker systems were, well, very resource intensive. One model averaged over 150 tool calls and took around 17 interaction rounds per task.
Wow, that's a lot of back and forth.
It is. In contrast, the top performers GPT-4o, o3, Qwen 3235B, often achieved similar or better results using far fewer resources, typically under 40 tool calls and maybe 6 to 8 rounds.
So the better models aren't just more successful, they're smarter about how they get there, more economical.
It certainly suggests that. Better strategic reasoning seems to lead directly to more efficient problem-solving, fewer wasted steps.
So putting it all together, the picture seems to be basic tool use mechanics are becoming table stakes. But the real challenge, the area where models truly differ, is in the intelligent planning, coordination, efficiency, and scalability needed for complex, multi-step, potentially multi-domain tasks.
That sums it up well. This deep dive into MCP-Bench really does illuminate the current state. LLM agents have come a long way in just interacting with tools, but the benchmark shows their abilities are seriously tested by the kind of fuzzy, interconnected problems we face in the real world.
It tells us that the focus is shifting, doesn't it? From just teaching LLMs how to use tools to teaching them how to think strategically about orchestrating solutions in these complex environments that MCP-Bench tries to simulate.
Mastering that higher order reasoning and planning seems to be the key path toward more autonomous and genuinely intelligent agents.
And the research suggests the future isn't just about throwing more tools or data at the problem.
No, it's about achieving deeper, more efficient reasoning. And that's the kind of capability gap that a rigorous benchmark like MCP-Bench is designed to expose, measure, and ultimately help the field to address.
A really insightful look at how we're measuring and pushing the boundaries of AI agents. Thank you for joining us on this deep dive. We hope you've gained a clearer understanding of the complex ways we evaluate these tool-using LLMs. It leaves you wondering, doesn't it? What truly separates simply using a tool from intelligently orchestrating a solution? Keep exploring, keep questioning, and we'll see you next time on The Deep Dive.